to one of the TAs. And
Yeah, they sent it earlier, and this was sent somewhere halfway through summer, right? So morning, everyone. We're going to have a few issues today because I cannot point because this magical laser pointer has neither a laser nor a pointer. So I'm going to try to point with my fingers. You're going to have to figure out what I'm pointing out to. So welcome to lecture 2 of Intro to Deep Networks. A quick recap, what we've seen so far. Neural networks have taken over pretty much all of AI tasks. Stuff like speech recognition, machine translation, playing games, even drawing art, self-driving cars, navigation. These things are being used in every possible AI problem that you can think of, and quite successfully. We also saw that in their basic form, these neural networks which perform all of these fancy tasks try to mimic the network structure of the brain. The brain, in turn, is composed of networks of neurons, and our model for it is going to try to emulate the structure. The individual neurons in the brain, the one that we have in the figure, have this have the property that they are connected to by many neurons. If the aggregate incoming signal exceeds some threshold, they're going to fire, and a signal goes down the axon down to our other signal. So our computational models have the same structure. Our basic computational unit is a perceptron, which looks like the figure to the left. The perceptron considers a weighted combination of all of its inputs. It compares it to a threshold. If the aggregate input exceeds the threshold, it fires, otherwise it doesn't fire. Now, the actual neural network itself is a network of such elements. We connect many of them up in order to get the more complex neural networks that perform these various tasks that we just saw. So here is the perceptron, the basic unit. It's a threshold unit. It fires if the weighted sum of inputs exceeds a threshold, and electrical engineers saw would call this a threshold gate. How many of you are electrical engineers? So you're familiar with threshold gates, right? So I've just redrawn the same figure. Instead of saying I'm going to compute a weighted combination of inputs and compare it to a threshold, I can say it somewhat differently. I can say that I'm going to compute a weighted combination of inputs minus a threshold and compare it to 0. So now it just becomes a sign operation. So stated, now the perceptron has just said that the perceptron simply says I'm computing an affine combination of the inputs. So how many of you know the difference between affine and linear? And what is the difference?
Affine also has a translation in it.
Exactly, right? So when I say something is linear, how do you define linear? Go ahead. Be brave.
Well, I guess like a linear operation is one where the argument, like the function decomposes over the argument. So you can take like a sum of like vectors in your vector space.
Yeah, so it's something that has this property, right? A times f of ax plus by is a times f of x plus b times f of y. And this obviously now, which means that f of x really should f of 0 must be 0. So this is like a hyperplane that goes through origin. So any relation which is of this kind is linear. Now if I and so a linear operation will have the structure summation I wi xi. If I add a constant to it, this equation now no longer goes through the origin. It's actually going to go off the side. This property will not hold. And so, but still, it has a basic linear property to it, right? This kind of relationship is what we will call affine. It's a translated linear hyperplane. So the way we define our basic unit is something that operates on affine combinations of inputs. And the basic unit as we first defined it is just a sign operator, meaning you look at an affine combination of the inputs and take the sign. The output is 1 or -1 or 1 or 0, depending on the sign of the input and how you define it. So we also saw that we can modify this basic operation a little bit and replace this thresholding sign operation by something that's softer, like a sigmoid, which instead of switching between 0 and 1 can actually sort of smoothly slide from 0 to 1. And once we figure that we're not really insisting on switching outputs, we can replace that function over there, which operates on the affine combination of inputs, using other functions like the ones I have in the figure, like the tan H, or the soft plus, or the half wave rectifier, which is 0 if the input is negative and equal to the input if the input is positive. All of these various combinations are possible. The only thing that changed between the original unit that we considered and this one is that instead of only considering a sign operator on the affine combination of inputs, we are willing to consider other functions. The multi-layer perceptron was just a network of such units. You took many such units, you connected them up. So I have two such figures over here. Both of them are multi-layer perceptrons. They're both very similarly structured. The fundamental difference between the two is that in one case there's only one output, in the other there are multiple outputs, but they're all the same basic structure. Now we are speaking of deep neural networks. Where does depth come in? What does it mean to say a network is deep? Does anyone have an idea? This term depth is actually very formally defined. Yes, Tobias?
Is it to do with the number of hidden layers?
Yes, but there's something more formal than that. How many of you have actually taken any course in graph theory? Surely there are some people who have taken some course in graph theory. Ahmad, you? Yes. What do you say? What do you mean when you say a graph is deep? Oh God. So, Sanan?
I also took the course with them, so I don't know.
This is terrible, right? So we speak in terms of depth anytime you have a directed graph. Directed graphs are going to have sources and sinks. And so you have two different directed graphs. Now, if I have a single source and you usually define it in terms of a common source, you can have multiple sinks, but say let's have a single sink. The longest path from a source to a sink is the depth of the graph. So over here, I have this figure to the left, and yes, something clicked in his head. Now, how many different paths do I have from the source? How many sources and sinks do I have in the graph to the left?
One, two, one each.
One each. And how many different paths do I have from the source to the sink? Two. And what are the lengths? Which is, what would the depth be? Two, because that's the longest one. The figure to the right? Again, I have only a single source and a single sink. How many different paths do I have? It's very simple. 3 of them, right? And what is the depth of this graph? 3, because the longest path goes up, down. And so although I do have paths of length 1 and length 2. So there's a very formal definition for the depth of a graph of this kind. And when I speak of a neural network of this sort, what do you think the depth is going to be when I define it like so? It's going to be the largest number of units. It doesn't necessarily have to be layered. I've drawn it in a layered manner, right? Basically, we are going from input to output. The largest number of neurons that any input signal must go through before it arrives at the output is going to be the depth of the network. So that's the depth of the network. But then formally, when I say a network is deep, I need to assign a number. When do I begin calling a network deep? If the depth is greater than 2, which means that if I have to process the input using more than 2 neurons before I get an output, I call the network deep. So there's a very distinct definition to this. Now, the way we saw define multi-layer perceptrons, they could operate on real or Boolean stimuli. The outputs could be real or Boolean. And you could actually also have multiple outputs or a single output. And what we saw that these kinds of networks can compute all kinds of stuff. Like, what are the kinds of input-output relationships we saw it could model? Anyone?
thresholding of thresholding of expressions.
We saw it could compute Boolean functions over Boolean inputs. We saw it could compute categorical outputs over real valued inputs. And we saw it could compute real valued outputs over real valued inputs, pretty much the entire class of functions that you would use in your day-to-day life, right? So we saw multi-layer perceptrons can approximate any functions. They can compose Boolean functions. They can compose real valued functions. And what were the limitations? There really weren't many, right? But because they could compute pretty much any Boolean function and any real valued function. So today we're going to pick up from this point. Yes?
What is this class of functions that they cannot approximate?
They are universal approximators, pretty much. So repeat the question at the end of this class. Okay? The class is all about why they are universal approximators. Now, multi-layer perceptrons as universal Boolean functions, as universal classifiers, and as universal approximators. That's what we're going to go through today. There is, towards the end, a bunch of slides on something called radial basis function networks, which I will not be talking about, which means, of course, it's going to appear in the quiz, right? Let's start with the very first topic, as universal Boolean functions. Now, how well do MLPs model Boolean functions? Remember? What kinds of Boolean functions can they model?
Except XOR everything else.
That's a single perceptron. What could a multi-layer perceptron model? Any Boolean function at all, right? There was no restriction on the kind of Boolean function it could actually model. So we saw that perceptrons, individual perceptrons, could be Boolean gates. We saw how the figure to the left, that was an AND, right? The figure to the bottom was an OR. The figure to the right was a negation. If I can perform these three functions, I can connect them up, and I can compute pretty much any Boolean function. In fact, if I can show you how I can compute a NAND. And if I have a NAND gate, do I need anything else to compute Boolean functions? No, because a NAND gate is a universal Boolean component. All I need is an AND gate, right? So, but they are much more powerful than just doing these simple Boolean functions. So consider this guy, right? This one is what I will call a universal AND. So I want to have a perceptron, which is something like this. I have the output Y. I have the first L, say x1 through xl, and I want all of these guys to have a value 1. And then I have the subsequent L plus 1 through n. I want all of these to be 0. I want the output to be 1 only when this wire is getting annoying. Okay. So I want the output to be 1 only when the first L inputs are 1 and the subsequent inputs are 0. Right? How would I design such a network? Such a unit? I claim it can be done. And the reason I claim it can be done is that that's really a linear function, a linear threshold. So let me see how this works. I'm going to apply a weight of 1 to all of these guys, a weight of -1 to all of these guys, right? So what happens if any of these is not 0? So let's see what happens when I get exactly the pattern I want. The first L are 1, the rest of the L are 0, right? The rest of the inputs are 0. In that case, what is the total weighted combination that comes inside? L, because I have L ones and the rest are zeros, right? So we know that if I use a threshold of L, the output is going to be a 1 for the correct pattern. Now what happens if I just flip one of the bits? What happens? Because, yes, if I flip one of these guys and I keep these as zeros, the sum is going to be less than L. If I flip one of these bits, because the corresponding weight is 1, and the input went from 0 to 1, that's going to subtract, and the input is again going to be less than L, right? So this means I have constructed a very, very specific unit that only fires for a very specific pattern of inputs and not for anything else. So that's a universal AND. I want all this combination to hold, and only then will it fire. So, you have a question? No, not you, sir. Shazab, the guy behind you, right? Okay. So here's another one, right? I have the same structure. I want the unit to fire if any of these first L guys are 1, or if any of the subsequent guys are 0. Right? So can I do that? And I claim that I can do this with a threshold of L minus n plus 1. Why would that be? So let's consider what happens if one of these guys is 1 and the rest of them, basically all but 1 bits are wrong. If all but 1 bits are wrong, right, we want only 1 bit to hold, correct? So that means I have amongst the first L, I have a single 1. Amongst the rest, they're all 1s. So if they're all 1s, I'm going to get these many minus 1s and a single positive, right? That's going to be L minus n plus 1. As I add more and more bits, that number is only going to keep increasing, right? Because now as I keep switching these guys off, the sum is going to keep increasing. As I keep switching these guys on, the sum is going to keep increasing. The only condition under which the input doesn't exceed the threshold is if none of the top L are 1 and none of the bottom L are 0, right? So this is a universal OR, meaning I can define an OR of any combination of inputs. So you really see that this basic unit is very, very powerful, right? I can even do something more interesting. I can say, well, I have a generalization of what I have. Negation is generally not a problem. We see that, right? If I want to negate an input, I just change the weight from 1 to minus 1. So negation is not a problem. So let's not worry about negation. Now, in this case, suppose I want to say that I want k of the n inputs to be 1. How would I do this? I just use a threshold of k, right? I want at least k of the inputs to be 1. I just use a threshold of k. If the number of inputs, which is 1, is less than k, it's not going to fire. Otherwise, it will fire. So this is what is called a majority gate. Because I can say fire if the majority of the inputs fire. Now, if I want to construct a majority circuit using standard Boolean operators, not a threshold gate, how many units would I need? If I want to construct I want to construct a Boolean circuit which says fire if the majority of the inputs is 1. At least L over 2 inputs are 1. Or fire if at least k of the inputs are 1. How many units would I need? It's going to be exponential in the number of inputs. You have to consider every possible combination and decide whether it's going to fire or not. Right? So it's going to be exponential in the it's large. So this is a single unit compressing an exponentially sized circuit into a single gate. You can see why Rosenblatt was fooled, that this was, a machine that's going to learn, talk, walk, and reproduce itself, because it can do stuff that would take an exponential number of gates if you wanted a standard Boolean circuit. And then, of course, Minsky and Papert came along and said you can't do an XOR, and the whole thing fell on its face. But then now we know that I can build an XOR by combining 3 of these gates, and it all works. Which told us that I can now, once I decide I can begin composing circuits by networking these guys, I can compose an arbitrary Boolean function. So MLPs, multi-layer perceptrons, are universal Boolean functions in the sense that they can compose any Boolean function. Now, in the Boolean function I have to my right and to your left, I have many layers of units, right? How many layers do I have? What's the depth of that circuit? 3, right? Please have a name tag so I know who you are, right? So And what about the one to the right? 4, right? So would I always need a depth of 3 for the Boolean function to the left? How many layers will I actually need to compute an arbitrary Boolean function? And I'm not going to wait for you to answer. I'll give you the answer. The answer is 1. One hidden layer, so 2 layers. A depth of 2 is going to compose any Boolean function. And to explain why, I'm going to present a Boolean function using a different format. What is a Boolean function? It's just a table, right? I can list out every combination of inputs and the corresponding output. So here is a Boolean function over 5 inputs. The column y is the set of outputs. I don't need to represent the combinations for which the output is 0. I only need to represent the combinations for which the output is 1. The rest are implicit, right? So this means this is a truth table, and a truth table is a complete characterization of a Boolean function. Now, if I give you a truth table, what is the simplest way of composing a function from this? K-maps.
Or a conjunction of this term.
DNF formula, right? The DNF formula is the simplest way of doing it. So I can just think of something like this. I can explicitly list out the input combinations for which the output must be 1. So here I have 6 combinations for which the output must be 1. It says the output must be 1 if x1 is 0, x2 is 0, x3 is 1, x4 is 1, and x5 is 0. Or in Boolean terms, not x1, not x2, x3, x4, and not x5. That's one conjunction that should actually produce an output of 1. Another one is not x1, x2, not x3, x4, and x5. I have 6 such clauses. And if I just OR these 6 clauses, I have completely specified this formula, right? So now I know exactly, given this, how would I compose an MLP to compose the circuit? Anyone?
Each perceptron is corresponding to one.
Exactly, right? I'm going to have one perceptron for this first guy because a perceptron is a universal, and another for the next, another for the next, another for the next, another for the next, another for the next. And then what do I do finally? I OR the lot. And voila. Now, this is true for any truth table, correct? So because this is true for any truth table, this means that I can compose any Boolean function using just one hidden layer. A one hidden layer multi-layer perceptron is a universal Boolean function. But then, what is the largest size of the network I would require if I want to compose a Boolean function using just one hidden layer? Kind of. Why?
Because you have 1 or 0 per input.
Well, that's not going to be, it's not that simple, right? So who said K-maps? Right, so there's at least one person who knows about K-maps. How many of you have heard of Carnot maps? Okay. A Carnot map is a different way of representing a truth table, right? A Carnot map is one where instead of just representing it as one table, I'm going to create a topological map, something of this kind. And so this is a truth table over 4 variables. The rows represent all combinations of 2 variables. The columns represent all combinations of the other 2 variables. So every box is a combination of 4 variables. If I highlight the box, that combination outputs 1. If I don't, that combination outputs 0. So this is a complete characterization of the function. Now, the way the thing is arranged is that the difference between any 2 adjacent columns is only 1 bit. So which means the 2 boundaries also attach. The 2 left and right boundaries attach. The top and bottom boundaries attach. So this actually represents a donut. And now I have a truth table with 7 elements. If I were to compose a simple DNF formula from this, I'm going to require how many clauses? 7 clauses if I do a basic blind composition, right? But then what I can do is begin grouping things up. And because of the manner in which I've composed this map, anytime I group a pair of adjacent elements up, I'm eliminating one variable. So look at this column. That column I have grouped. What that group is telling me is that it does not matter what the values of w and x are. The output is going to be 1 so long as y and z are 0, 0. Right? So that entire group is now just a single clause, not y, not z. And so I can begin grouping things up. And what was 7 clauses just became 3 clauses. Now, trying to find the most compact grouping of units in a Carnot map is an NP-hard problem. So it's not like it's trivially solved. But the point, more importantly, for many, many functions, you can begin grouping things up, which means that how many perceptrons would I need in the one hidden layer if I wanted a single hidden layer network for this guy? Just 3, right? That's going to be my function. Did I get it? Wait. Something happened here. Just this one, right? So easy enough. Why could I do this? Because I could begin grouping things up. Now tell me, let me go back to my original Carnot map. What is the worst case? For this guy, what is the worst case for the number of units I would need in the hidden layer? 16? Because if it was 16, I just group them all up, right? I need a chessboard. If I have a chessboard, I cannot group anything at all. And if I cannot group anything at all, I'm going to, how many units? I'm going to need 8, right? Let me go this, so this guy is going to require 8 units in the one hidden layer. Here is a 3-dimensional equivalent of a Carnot map, a 3-dimensional Carnot map. This is over 6 variables. Now over here, this too is a chessboard, right? I cannot group things up. How many units would I need? 32 in the hidden layer. Correct. So there are 64 combinations. 4 times 4 times 4, 32. So in general, I'm going to require 2 raised to n minus 1 units in the one hidden layer if I decide I'm going to compose this function using just one hidden layer. Right? So the worst case for trying to compose a Boolean function using a one hidden layer MLP is exponential, and the size of the inputs, it's not 2 raised to n, it's 2 raised to n over 2. Right? But then what else can you tell me about these patterns? Do I really need that many units? If I allowed you to go deep, how many units would I need? Can you think about that? So I've given you the requisite 30 seconds. Let me answer for you. I expect faster answers, guys. These are XORs, right? The figure to the left is W XOR Y, X XOR Y XOR Z. The one to the right is U XOR V XOR W XOR X XOR Y XOR Z. Now, how many units do I need? How many units do I need for an XOR? 3. Actually, I need 2. Right? I can do an XOR using just 2 MLPs, 2 perceptrons. The 3 is an easy way to an easy design, but because I'm allowed to use fractional thresholds, I can actually construct an XOR using just 2. I'll continue to assume that we can use 3. We're going to use 3 in my the rest of my slides. But then this guy can be constructed like so, right? I can just have 3 for every XOR in the function, which means that I'm going to do this in this case. I have 3 XORs. So for each XOR, I'm going to need 3 perceptrons, actually only 2. So this means I can do this with 9 or even 6 perceptrons. For this function, I can get away with 15 or maybe 10 perceptrons, right? You don't see the difference. It's not very much. In the first case, it was 6 versus 8, no big deal, right? Here it's 10 versus 32, still no big deal. What happens when I go to a 100-dimensional input? It's going to be 2 raised to 99 versus 2 times 99. Correct? So more generally, the XOR of n variables is going to require 3, actually 2 times n minus 1 perceptrons. And so something that requires an exponential number of units, if you're trying to do this with just one hidden layer, is going to require only a linearly sized circuit if you allow it to go deep. So you can see why depth matters, right? Now, there's more to it than that. It's not just such naive explanation. So let's go. So when I begin XORing things, the way I did it is I just kept adding layers, right? I XORed one, then I added another layer, then I XORed the next, and XORed the next, and XORed the next. I don't need to do that. I can group things up like so. So we know an XOR is associative, which means I can group things up pretty much in any which way. So if I want to do x1 XOR x2 XOR x3 XOR x4 XOR x5 XOR x6, what I can first do is to XOR these two guys, which is going to need 3 units, correct? Then I can XOR these two guys, which is going to need 3 units. And then at some point, let's say I had 2 more, I'd XOR all of them, and each of them are going to need 3 units. Now, so I have partial values out here. What is the relationship between these guys that I must compute in order to compute the final output? It's an XOR again. So now, same thing. I can keep doing this, right? So which means that the number of layers I'm going to require is log 2 of n, right? Or 2 times log 2 of n, to be more precise. So this, I can actually do this in order log 2 of n layers. What happens if I decide I'm allowing depth, but I'm only going to use k layers? I've put an upper bound on the number of layers I'm willing to accept. What would happen? What happens here? So let's say I decide I'm going to add 3 layers instead of 2, right? Then if I say 3, I'm stuck with this guy, right? From here on, I'm only allowed to add 1 more layer. How wide would that layer be? Exponentially wide, because now I have XORs again, correct? So anytime I say I have a fixed number of layers, from that point on I have a complex XOR function, and I'm trying to represent that XOR function using just 1 more hidden layer. And we know that if I try to represent any XOR using 1 hidden layer, it's going to be exponentially wide. Make sense to everyone? Right? And so if I decide that I'm going to have a fixed number of layers, if I fix the number of layers, then the circuit is always going to be, the worst case circuit is always going to be exponentially wide. Right? Now, and it actually, you can skip the text on it. You can look up the slides later, but you get the idea, right? So now I've been speaking entirely in terms of perceptrons. What you really want to worry about is the number of edges in the circuit. And why is that? Because when you build a circuit, it's really the number of connections that specifies both the circuit complexity and the arithmetic complexity. So it's the number of edges that you're really worried about. But then, and the number of edges can be super exponential if the number of perceptrons units is exponential. But for convenience sake, it's convenient to continue to think of the number of units rather than the number of edges, because for things like XORs, the number of edges is linearly related to the number of units, right, in the correct architecture. So deep Boolean MLPs that scale linearly with the number of inputs become exponentially large if recast using only 1 or even any fixed number of layers. Make sense to everyone, right? And it gets worse, right? I can have some complicated function which is an XOR after some number of layers. At the point where it becomes an XOR, from there on I'm going to need many, many more layers, but the number of layers depends on the number of clauses over which I'm performing the XOR. So the problem over here is the depth of the network depends on the function, right? Different functions require different depths. You can't just say use a fixed depth. If I decide that I'm going to have a fixed depth, and if you try to learn an arbitrary unknown function, you would be able to do this properly for some functions, but for the majority of the functions, they're going to be more complex than that. And you're not going to do a right job, right? Now the reason I chose an XOR as an example is very simple. If I think of an XOR as a classifier, what happens if I just lose one bit? What does the accuracy become? Yeah. If I just lose one bit, the XOR is going to be wrong half the time, right? So an XOR is a very, very delicate function. It's one bit that kills the function. That's why I'm using an XOR. It's an extreme case of some kind. Think about it carefully offline, right? If I flip a bit, if I just delete a bit from my input, then the plane becomes wrong half the time. So the XOR really, if you want to talk about it formally, the XOR is really a parity problem. And it turns out any Boolean circuit of depth D, which uses only AND, OR, and NOT gates with unbounded fan-in, must have a size of 2 raised to n raised to 1 over D in order to be able to have, which basically means that if you fix the depth, so when I fix the depth to D, and I say this is the depth D, then the size actually becomes exponential in n, right? The only way you can actually keep it limited is if D is a function of n, in which case n raised to 1 over D can become a constant, right? So, or n raised to 1 over D can become something manageable. But if you fix D, then it becomes exponential in n. So this is, how many of you have taken any kinds of courses on complexity theory? So what kind of complexity theory, circuit complexity, what class of functions would that be if I fix the depth?
Which one? If D is dependent on, is a function of n?
If D is fixed.
If D is fixed, then it would be, exponential.
So that's an AC0 circuit class, right? Arithmetic circuit 0. So we have, just as you have complexity theory, which depends on, talks about it in terms of computational complexity, you also have circuit complexity. If I want to build a circuit, how many units do I need? AC0 is basically what most of the stuff we use is, because in practical terms, you really want to fix the depth. You're not going to have a circuit whose depth keeps changing with the problem. You build a computer, there's only so much you're going to put on the processor or in the computer. So real world circuits are all AC0. And the fact of the matter is that parity, it doesn't belong to the class of AC0. It actually gets much more interesting than that. So again, not all Boolean functions have such clear depth versus size trade-offs. There's a anybody from IITs? Okay, so you must have, which one? Okay. You must have probably encountered Shannon's theorem on circuit size, right? Logic design, right? This is, we cover this in India, standard theorem. Shannon has a very nice little theorem which says that for n equals greater than 2, there does exist a Boolean function of n variables that requires at least 2 raised to n over n gates. Now, it's actually, there's more to it than that. The majority of Boolean functions, what I mean by majority is that basically with a probability approaching 1 for large n, any Boolean function that you pick is going to require 2 raised to n over n gates. Pretty much all Boolean functions require an exponentially large number of gates, regardless of the depth, right? So I actually talked about a very small subset of Boolean functions, and even there, we begin to see how depth really matters. So, in summary, an MLP is a universal Boolean function, can represent a given function only if it's sufficiently wide, it's sufficiently deep. Depth can be traded off for exponential growth of the width of the network, and optimal width and depth depend on the number of variables and the complexity of the Boolean function itself, right? So I'll skip the summary slide because I'm running out of time. I may just run a little over because we had some starting troubles. We got started 10 minutes late. There's a second caveat. I used a Boolean circuit as an analogy for explanation, but really, are we dealing with Boolean circuits when we're talking about multi-layer perceptrons? We're dealing with threshold gates, right? threshold gates are much, much more powerful than simple Boolean gates. So threshold gates, we saw that a single threshold gate can perform an operation that would require a circuit network of exponential size if you're thinking of it in Boolean terms. So it's not very clear how exactly to analyze circuits of threshold gates, but in general, there's a lot of proof that for large n, for large input, for most Boolean functions, a threshold circuit that's polynomial in n at optimal depth can become exponentially large in the number of units if you just reduce the depth by just 1. Which again goes back to say that if you fix the depth of the circuit, if you fix the depth of your MLP, then the vast majority of functions that you would like to express with it are not going to be expressible. Right? But deeper is always better. Every time you add one more layer to your MLP, the number of functions you can actually express with it grows exponentially. Questions? No? Okay, great. So we've been talking about Boolean inputs, right? But what do we actually operate on? Most of the time we're operating on reals. And that is this business of classification as opposed to performing Boolean computation. We've seen already that MLPs are functions over real inputs. What an MLP really does is to find a complex decision boundary over a space of reals. If you're using it as a classifier, it's supposed to produce a 1 inside the boundary and 0 outside. Now, an individual perceptron, we saw this in the last class, is simply a linear classifier. It uses a linear threshold, which is a hyperplane. The output is going to be 0 on one side, 1 on the other side. So if the input were two-dimensional, the perceptron is going to be a function of this kind, right? And we saw immediately, once I just know that this is what a perceptron is going to compute, I can compute ORs, ANDs, negations. What I cannot compute, Steve, do you mind shutting the laptop? So, and you guys can shut the laptop? I did mention that there's a strictly laptop shut class, right? So, bear with me. Now, from this, you can actually see why this is not going to be an XOR. Why? Because an XOR is not just a step function. An XOR is going to go up across the diagonal and then come back down once you get past the diagonal. So this is why a perceptron, no matter how complex you make this perceptron, is never going to model an XOR. A perceptron is only capable of linear boundaries. But then, of course, we saw immediately in the last class how I can begin composing random decision boundaries. A pentagon, I just have one perceptron each for each of these boundaries, and then I'd AND them up, and I'd get a single, my pentagon, right? So now observe something. I want you to keep track of something. This sort of gave you the impression that I can compose any polygon using an MLP, correct? And the polygon has a characteristic. It is convex. Does this necessarily mean that a circuit of this kind with one hidden layer and a single output can only compose convex polygons? Can you look at this figure and tell me how you can give me a decision boundary that's not a convex polygon? Yes, yes, that. No, I'm just saying, just this circuit from this guy. How can I get something that's not a convex polygon? Yes.
You have like a Caesar shape.
How? What happens if I use a threshold of 4 at the output? What is the boundary going to be? It's going to be a star, right? So don't imagine just because I drew pretty convex polygons that it can only model convex polygons. It can actually model non-convex shapes as well, right? If I use a threshold of 4, this function is going to look something like this. There was your pentagon, but this, so the sum over here was 5. the sum in these regions was 4, correct? Elsewhere it was less than 4. So if I use a threshold of 4, I'm going to get a star. If I use a threshold of 3, I'm going to get some other shape. So it's not restricted to convex shapes. Regardless, there's no construction of this kind that I can use that's going to give me this function. I can guarantee it. I can prove it mathematically. There's no way I'm going to be able to get this polygon, this double polygon, right? So in the last class, I sort of hand-waved enough to give you this quant notion that I can just that I can only construct polygons. That's not polytopes. That's not true. I can construct non-convex shapes. Regardless, there are shapes I will never really be able to construct, and this is one of those. And why would that be? Because regardless of what threshold I choose, I have a bunch of decisions. They're all going to be adding up. And by changing the threshold, I can get different shapes. There's no threshold that's going to give me this double polytope. And I can prove it, right? But let's not bother about proving it. That's not what this class is about. You just take my word for it. And if you really, really, are fixated about it, you can go off and try to figure this out. But then we know how we can design this guy by adding one more layer, and then I get this double polytope. And now I can compose things of this kind. And the way I would do it is, if I wanted to build this decision boundary to the left, I'm going to chop it up. I'm going to chop it up into polytopes simply because they're kind of convenient. And then I can have one little subnetwork for each of those components. I can OR the lot. I'm not ANDing them anymore. I'm ORing the lot, which says that if I'm in any of these regions, I'm within the greater outer region. And now I can compose the larger structure, right? So this means I can compose arbitrary decision boundaries. But tell me, can I compose an arbitrary decision boundary using only one hidden layer? We saw we can do a star. I want you to do this guy using only one hidden layer. How would you do it? Anyone want to take a guess? Okay, the requisite 30 seconds. And it's not an easy answer, right? What about this one? I just told you it's not possible, right? Not with 5 units, but instead of 5 hidden units, suppose I allowed you to use 10, could you do it? If I allowed you to use 20, could you do it? How many hidden units would you require to be able to do this using only one hidden layer?
The Boolean combination of x1 and x2 that are in the boundary. So that would be, if it's real space, then it's just infinite.
Thank you, right? It's going to be infinite. And I'll explain to you why, right? Perhaps you can say this aloud.
What I just said?
Yeah.
You need to basically specify all the combinations of x1 and x2 that will be true, like a Boolean function. So if it's a real space, then the combinations are basically infinite. So it'll be infinite perceptron.
You can do this with one hidden layer. That hidden layer is going to be infinitely wide. But if I decide that I don't want exact precision, I can approximate it. I will still need an arbitrarily large number of perceptrons, and I'm going to explain to you why. Okay? Let's start off by composing a diamond. So if I'm doing a diamond, if I have four perceptrons, the sum is going to be 4 in the center. It's going to be 3 in the yellow regions. What is the extent of the region where the sum is 3? It's infinite, right? It's these infinite strips. And so the sum itself has a shape that looks like the thing to the right. Now suppose I want to do a pentagon. I have 5 lines, so I have 5 perceptrons. The sum of the 5, outputs of the 5, looks like the figure, with the interesting figure I have to your right. And so the region where the sum is now 4, so if n is the number of sides, when n was 4, the area of the region where the sum was n minus 1, namely 3, was infinite, right? When n became 5, the area where the sum was n minus 1, 4, became finite. Now if n is 6, the area where the sum is 5 becomes smaller still, compared to the 5. And now keep looking at the figure to the right. Look at what it looks like, right? And then here's what I get with a heptagon. This is where I get the sum. Here's where I get something with 16 sides. Here's what I get using 64 sides. Here's what I get using 1,000 sides. Here's what I get with a very large number of sides. In the limit, it's going to look like the figure out there. And you can derive the nice little formula for this, which is there, which is on the slides. The formula is kind of fun to derive. This is second-year college math. But it's not the formula that's important. What is really happening is that as I keep increasing the number of sides, I'm going to get a cylinder-like shape where the sum is n in the cylinder, and then it tapers off very fast to n over 2 off to the sides. And if I manipulate the radius of the cylinder just right, then I'm going to get something which almost looks like this when zoomed in, which is n in the center and just falls off to n over 2 very fast off to the side. And I can actually add a little bias term over here so that now it's n over 2 in the center and 0 in the sides. I'm just subtracting n over 2 from everything, right? But here is the beautiful thing. Once I can do this, what have I really constructed? A cylinder. If I use a threshold of n over 2, I'm going to get a decision boundary that's a perfect circle, right? But I can now take two of these circuits and sum them up, sum their outputs up. And because outside the cylinder the sum was 0, I'm going to get a figure with two disconnected circles, two disconnected cylinders. If I apply a threshold of n over 2, the decision boundary is going to be two disconnected circles, because one of them constructed one cylinder, the other constructed the other cylinder, right? And so that means I can fill this guy up, right? And I can make this approximation arbitrarily precise by making those guys smaller and adding more and more of them. So I can decide how correct I'm going to be, and I can decide, and I can compose a circuit for this purpose. What this really means is that MLPs, a one hidden layer MLP can model any classification boundary with arbitrary precision, but it's going to require an exponential number of, or an extremely large, the number of neurons is going to approach infinity, right? So the trade-off here is that if I just decide to add 2 layers or one more layer, the number of neurons I needed to model that to any degree of precision just went from being ridiculously large to something I can count on one hand, right? So now formally, analysis of this kind of these kinds of networks views these as a category of arithmetic circuits, and there are various kinds of papers on this that we don't need to get into. I just was trying to convey the idea of the notion of depth and the importance of depth. But there's a beautiful paper by Leslie Valiant et al. Which shows that a polynomial of degree n, so if the function that you're trying to model is a polynomial, it could be a Boolean polynomial, you're going to require a network of depth log n squared. And if you use less than that, then the circuit is going to become exponential in size. So also Benjo et al. Show the same thing for Benjo's paper is a special case of Valiant's paper, right? So we've seen this in the case of a generic network. I gave you a very arbitrary function, and you got the idea. But then let's try to make it a little more concrete, right? Let's take something for a very specific pattern. I want to generate a decision boundary which is this checkerboard. It's in 2 dimensions, right? If this is in 2 dimensions, if I want to do this using only one hidden layer of neurons, how many neurons would I need in the hidden layer? Going by just what we just saw, you would believe that you can achieve arbitrary precision by using an arbitrarily large number of neurons in the hidden layer, right? Well, not entirely true, but for the purpose of this discussion, let's assume that's true. I'm saying not entirely true because this is in 2 dimensions, so there's something special about it. But now, if I decide that I'm going to add one more layer, I can do this with only 56 neurons. Why is that? Yes? Anybody else? So I'll tell you why, right? The basic circuit, the basic pattern is composed of 16 lines. So I need 16 neurons in the first layer, and I'm going to capture each of those 16 boundaries. The actual pattern is 40 blocks over those 16 boundaries. So which means I need 40 neurons in the second layer, 16 in the first for each of the lines, and then I can OR them up, and that's going to give me this circuit, this pattern, right? So I need 56 hidden neurons. But if I want to do this with more than 2 layers, how many layers, how many neurons would I need? We've just seen this, right? This is an XOR. So this is an XOR over all of the 16 lines. I need 15 XORs. 15 XORs is 30 neurons over the 16 lines, so 46 neurons is going to do it. The difference is not very large. I can, well, I'm saying 61 over here because I'm assuming 3 neurons per XOR, but I can do this with 36. But if I have something like this, again, the one hidden layer neuron network is going to require infinite neurons. But it's 64 basic linear lines, and so there are something like 544 boxes in this. So the total circuit in 2 layers is going to be 608 hidden neurons. But if I did this using an XOR, that's going to be 16 times 15. So this actually is 64, right? 64 times 63 times 2. So 126 plus 64, which is a very small number of neurons. If I want to do this using an XOR circuit. Again, we see that depth gives you a lot of benefits over even low dimensional spaces, functions, when you actually, as opposed to having a fixed depth network. So skip this here. Now, the number of neurons required in shallow networks is potentially exponential in the dimensionality of the input. And this is the worst case, of course. Alternately, it's exponential in the number of statistically independent features that you've got in your input. So that is if you decide that the network is going to be shallow. And by shallow, I mean anytime you fix the depth of the network. It's shallow for a very large class of functions, right? So story so far, MLPs are Boolean machines. Even a network with a single hidden layer is a universal Boolean machine. Multi-layer perceptrons are universal classification functions. Even a network with a single hidden layer is a universal classifier. But a single hidden layer network may require an exponentially larger number of perceptrons than a deep one. And deeper networks may require exponentially fewer neurons, conversely, to model the same function. So what about as universal approximators? These are all functions where the output was Boolean, right? So we also saw that how it could model real valued functions. We saw this for the case of a function of a single variable. So if we were trying to model y equals f of x, where x is just a single variable and y is scalar, then we saw how I can just compose a little network of 3 neurons. I get a step function, and then I can patch a bunch of these together and approximate any function to arbitrary precision. How would I do this for more than 2 dimensions? If your answer is that I'm going to begin putting cubes, your answer is wrong. The way you would do it is that the realization over here is that a step function is a specialization of a cylinder. So now I know how to compose a cylinder, which is n over 2 in the center and 0 on the sides. So if I want an arbitrary function, I fill up the space with cylinders, scale them to different heights, and add them up, and I can compose pretty much any real valued function to arbitrary precision using just one hidden layer, right? So that's the magic. These things, even a one hidden layer neural network, uses a universal approximator. It can approximate. Advait, you had the question, right? So did this answer anything? Answer your questions? Yes, okay. So even a one hidden layer MLP is a universal approximator. It can model pretty much any function that you want. So thing over here, I call it a universal approximator, but I assume that all of these subcircuits, the outputs of all of these subcircuits are being added. When we looked at perceptrons, what did we really have? you had an activation function operating on the affine combination of inputs, right? So when I include an activation function, the final network perceptron, the final unit in the network, has some activation function that's operating on the affine combination, which could be a sigmoid, a tanh, a soft plus, a rectifier, whatever else. And that activation function is going to have a codomain, a range actually, the range of values that it can produce. And so what a multi-layer perceptron really is a universal function, universal map from the input space to the range of the activation function in the output layer, right? So you're specifying the input space, which is Rn. The output space is going to be some subset of Rk, where k is the number of outputs, and the subset depends on the range of values that the output activation can produce. And once you fix these two, I can take any function at all between these two, any map at all between these two, and an MLP can model it, to be very precise. So that is to answer that, right? Okay. So an MLP is a universal approximator for the entire class of functions that it represents, the specific maps represented by the inputs and the output activation. So we've seen that deeper functions are better, but a shallow function can compute anything, right? But are there any restrictions? What are the restrictions? To look at these, let me just jump quickly to the example because we're running out of time. So look at this figure again, right? This figure, we said a neural network can represent any function, but provided it has sufficient capacity. What do I mean by capacity over here? So let's assume again, continue assuming that my activation function is a threshold. So if my activation function is a threshold, what are the kinds of decision boundaries it can produce? It can actually produce these step functions, right? Each perceptron can produce a step function, which is a 0 on one side of a hyperplane and a 1 on the other side of the hyperplane. So given that, this circuit, this pattern, if I agree that I'm going to use 2 layers, is going to require 16 neurons in the first layer and 40 in the second. If I decide that I'm going to use less than 16 neurons in the first layer, can I somehow compensate for this by having more neurons in subsequent layers or more layers? So if I decide that I'm only going to use 8 neurons in the first layer, is there any magic I can perform to still compute this map?
Change the threshold of the subsequent layer.
Anybody else? I saw you nodding. You're missing your name board. Yeah. What's your name? I'm sorry. Yeah. So, anybody else want to take a guess?
It would be arbitrarily large, right?
How large? Sanan? You cannot do it. Why is that? Okay. Again, remember that I'm assuming threshold activations, correct? So let's say my 8 lines, the 8 perceptrons in the first layer captured those 8 lines. So once you cross the line, you have no information about how far away you are from the line, right? The only information you're going to have is about where you are, which of those bands you're in, but within the band, all information is lost because the outputs are binary, right? 1 or 0, which means, or even if my perceptrons were to capture some kind of combinations and magically they figured these 8 lines out, the only information I am going to have is about which particular diamond the input is in, but within the diamond, all resolution is lost. Make sense to you, right? It doesn't matter what I do subsequently. I am never going to recover. There is no way of recovering from extracting insufficient information from the input, right? So same thing. I can have 5 million neurons on the first layer, but if the next layer has less than 40 neurons, which is what I'm going to require to capture the 40 boxes, it's not going to be able to capture the pattern, right? So the statement we're really saying is that it's not sufficient to have the right number of layers. Every single layer has to be sufficiently wide to capture all the information required from that layer, right? Is this a universal statement? Is this always going to be true? Or is it dependent on some assumption I just made? The threshold activation function. The problem was I decided that once you cross the boundary, it didn't matter, right? It couldn't tell you how far away you were from the boundary. And that is a problem, right? So so the sufficiency of architecture that we spoke over here was related to the fact that we were using a threshold activation, which didn't tell you how far away you were from the boundary. But then suppose I use a sigmoidal activation. The sigmoidal activation is going to tell you how far away you are from the boundary until a point, till the sigmoid saturates. So for some time, you continue to have information, and then that means that I can actually pass that information downstream, and the subsequent layers downstream can actually operate on this and still recover information. But now it means I have to add more layers to the circuit to be able to extract the information from the input that has been passed through by the lower layers, correct? And now there's more to it than that. Suppose if I decide that I'm going to use fewer than the minimum number of units in the first layer for this particular problem, right? So, sorry. So I give you a choice. So let's say this is my boundary, right? And this is my boundary. So one of these activations, one of these functions did something like this. Okay? So here's another boundary. The other function did something like this. Okay? So what happens over here? Once these things saturate, information is lost. So you're only retaining information close to the boundary, not very far from it, right? So given a choice between an activation of this kind, an activation of this kind, and an activation of this kind, and an activation of this kind, which of the three would you choose? The third one, why? It continues to retain information. It has managed to capture the boundary. It has different behaviors on either side of the boundary, which is very critical. We're basing the entire operation on the ability to capture boundaries, right? But then you would like to have information continued to be passed on. So if it were perfectly linear, would that be a good thing? No, because you lost the boundary. You have no way of knowing where the boundary really lay. You do want to capture the boundary, but then, or at least a boundary, right? But then you want to pass information on so that additional boundaries could be captured downstream. So in that sense, if I were building a network, I can actually have fewer than the requisite number of layers and requisite number of neurons in any layer, provided my activations forwarded information on. Which is why if you actually look at modern neural network architectures, people don't really use sigmoids because sigmoids saturate. And in the early layers, if sigmoids saturate, they're not going to be passing information on, right? In the final layer, of course, you have to make decisions. There are things you can do. But when you're passing information downstream, if you want to compensate for the fact that maybe your network is not sufficiently broad, you want to be passing information through, and clearly in that kind of situation, something like this or something like this is going to be a lot more effective than just either a threshold function or a sigmoid. That doesn't mean that threshold functions and sigmoids are bad activations. It just means that you're going to need a lot more neurons with those guys, right? This is true. We are not speaking of learning over here. We are speaking of representing a function. Right? Questions?
Can you reiterate why the linear would be worse than the third one?
The linear doesn't actually give you, the linear is not taking any kind of, it's not really modifying the input. So what we want to say, we are trying to demarcate specific locations in the space where behavior must change. So all of these are capturing a boundary right here. Right? A linear, can you tell me where in this input, where's my chalk? So if this was my activation, where's the boundary? There is no information, right? It's like not having that perceptron in the first place. This is just the affine combination, right? So we'll get back to those in a later lecture. So the point is that continuous activation functions result in graded output at the layer, and the gradation provides information to subsequent information layers to capture information missed in the lower layers. That is, it passes information on to subsequent layers, and activations with more gradation, like the rectified linear unit, can be expected to be more effective at passing information downstream while actually also capturing a boundary. Right? So narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded, but then in order to operate on this, you're going to need more layers, greater depth. So to kind of summarize, I'm speaking of a sufficiency of architecture. The capacity of a network has various definitions. They have things like information storage capacity, which is how many patterns it can remember. If you're working with machine learning, people like to talk about VC dimensions of classifiers and so on. From our perspective, the capacity of a network is to actually the ability to capture kind of different partition a space into different regions, and how many different convex hulls it can actually partition the space into, and how effectively it can do so. So formally, of course, this is a very informal way of thinking about it. If you want to be formal, you need better characterization. And it turns out there's really no nice way of characterizing the capacity of a network. So pretty much everything that we did in this class was supposed to give you an idea of the fact that a network has a capacity to model things. And if the function that you're trying to model is more difficult than what the network can model, then you can be arbitrarily wrong when you're trying to model it. And we also saw that different ways of improving the capacity of the network is making them broader, making them deeper, having activations which are more graded, so that subsequent layers can actually operate on these. We saw that if you lose information early, you are never going to recover, so you must try to do your best to not lose information early. Nevertheless, simply passing stuff on wholesale is not really achieving anything. You really need to be taking decisions at each point, right? Formally, of course, there's a lot of work on VC dimensions of networks, separate lecture. Koiron and Sontag had a very nice paper in 1998. Harvey, Love, Mehrabian had something more recently. Gerald Friedland and Krell had a really nice recent result. I hope to have Gerald Friedland come down later this semester to do a guest lecture on this work, where they showed how you can actually compute the capacity of a network when you think of it in threshold terms. And they have some excellent results. And particularly, they have results which show that how, no matter what you do, the network is always going to be wrong, right? And it can be wrong in really bad, malicious ways. So I'll stop right here, just slightly late. MLPs are universal Boolean functions. They are universal classifiers, universal approximators. A single layer MLP can approximate anything to arbitrary precision, but could be exponentially or even infinitely wide at in its input size. Deeper MLPs can achieve the same precision with far fewer neurons, which means the deeper networks are more expressive. What do I mean by expressive? They can model more types of functions, right? And next, we know that MLPs can emulate pretty much any function, but then how do you actually make them emulate a specific function of choice? We will look over that in the next 4 or 5 lectures. Questions? Yes.
In the general case, given an arbitrary region of space, can we predict what network size will be sufficient?
It's not the region of the space, the function, right? And so in the most general case, the answer is it's going to be exponentially large. That is basically Shannon's theorem, right? All you're always going to be doing is to approximate the function. You always have the issue that in real life you don't really know what function you're approximating, but even if you knew it, in the general case you can believe that you can only sort of get close to it, you're never going to exactly get it.
So in real world scenario, is there any reason apart from compute cost that we try to limit the number of layers?
Well, it doesn't matter. You're not going to have infinite layers, right? Anytime, regardless of the limitation you have, there's an infinitely large set of functions which is going to require more.